Good afternoon to you again. Now, today we'll look at something which is also very new after the excellent talk by Professor Larissa. And that is, we'll see something about dark energy and we'll see something about black holes. They are not that new as topics, but latest findings make them very interesting. As Professor Larissa said, in 1997, I had proposed a model
Published in
1998. 1997 it was proposed.
Yes.
And this was a model which went against the accepted wisdom. The accepted wisdom was that the universe is expanding, no doubt, but it is slowing down because of the gravitational force of all the objects inside. And one day it would come to a halt and then collapse. At that time, this paper of mine was suggesting quite the opposite. Namely, that not only would the universe not come to a halt, but rather it would go on accelerating, albeit very slowly. Now, nobody was more surprised than myself when the paper was accepted, because it is like saying that the crow is white and not black.
Yes.
There, what is called the cosmological constant was very small. It was of the order of the square of the Hubble constant, which itself is small. This signifies a very, very slow acceleration. Well, the very next year, observational astronomers from Australia and USA independently confirmed that the universe is accelerating very slowly. They observed what are called supernovae and seeing how they expanded, because supernovae are exploded stars, and how they were moving away from us. So suddenly a new paradigm had come into literature, into what people were talking and thinking, and that was dark energy. Next. All this was because dark energy, which seemed to be a fanciful thing, was observed. And observation is the final test. However wonderful the things we may talk, if they are not observed, it goes into the realm of speculation. Maybe, may not. And I'm sorry to say, one topic which is in such a realm is dark matter. We are talking about dark matter for the past 75-80 years when it was first proposed. But till date, there is no definitive observation of dark matter. Now, this model of 1997 also brought back to light some puzzling relations that were observed by a number of great thinkers and astrophysicists of last century, like Hermann Weyl, ending up with Paul Dirac, who got the Nobel Prize. Now, these were relations which linked up various cosmological parameters like the radius of the universe, the number of particles in the universe, the age of the universe, and so on. There were some relations which were ad hoc. That is, they were observed relations, but nobody knew why. And after some time, people started saying that these are just accidents, pure accidents, that one person's height equals another person's height. It's accident, it need not have been so. However, in this model, these relations were deduced on the basis of theory. And that theory contained what we today call dark energy, though dark energy is a later name. Now, I must say that like dark matter, till today, there is no unanimity about what exactly dark energy is. We know that there is dark energy, because of which the universe is accelerating. But what is it? There have been any number of theories. Many people have come forward with many models, none of which have led anywhere. We are no wiser, no way of saying that this is the model and that is not the model. Next please. So I will not go into the details of the various models for dark energy. Next please. Next, these are all the various theories which are prevalent today. People are writing large numbers of papers on all these various ways of looking at the dark energy, if you want to put it that way. Next please. Again, a description of the various models. Not very interesting. Please go. Then also string theory got into the act. They also had their own ideas about it. But the point is, none of these lead to any observational clues. It can be so, but do we know that it is so? Is there something in nature which we can see, which will tell us that this is it? There is no such clue. Next please. Now, in my original work, the candidate for dark energy was very humble, not anything grandiose, but something which we have known for much more than 100 years. And that is something which is called the zero-point field, or the energy of the quantum vacuum. You see, we are told that if there is no force acting on a particle, Newton's first law, then if the particle is at rest, it will continue to remain at rest. It will need a force to get it going. For example, just think of a pendulum. Let us assume that the pendulum has no weight, all those standard assumptions. Now, if this pendulum were there in outer space, no gravitation, no force, nothing, then what will happen to the pendulum? It will just remain there. It can't really go up or down or anything. If you actually perform this experiment in outer space, far away from any matter and so on, you will not see this. You will see something very dramatically different.
Some of you have seen the punching bag of boxers. When boxers do their training, they punch on the bag, and the bag can go this way, that way. That's exactly what will happen to this pendulum. It will move in a random manner. So, the pendulum is not at rest. Even in vacuum, it is just jiggling about in a very random manner. This is because what we called vacuum is not what we think vacuum is today. There are forces in vacuum, and these forces are the 0-point forces, which are fluctuational. They are not like Newton's laws or Newton's force that it will work in one direction and so on. So, the 0-point field leads to some very well-known phenomena, some of which you have heard. Let's skip all this, but one of the interesting manifestations of the 0-point field is what is called superfluidity. It's a bit like this pendulum. Suppose you take a liquid and keep on decreasing its temperature, and you reach very, very close to what is called the absolute zero. Now you know that at absolute zero, you wouldn't have any pressure, nothing. No temperature, no pressure, nothing. So nothing much should happen to the liquid, which is at absolute zero or very near. On the contrary, and these are experiments performed with liquid helium and helium-3, as you reach absolute zero, instead of just remaining still, the liquid behaves in a most peculiar manner. The liquids are usually in a glass tumbler, let us say. Suddenly the liquid starts rising up, defying gravity, or going sideways. This is called the superfluidity of helium, first seen for helium-4 and much later for helium-3 by Professor Douglas Osheroff, who had come here and given a stimulating lecture. So think of the 0-point field as such a residual, indescribable force which is there even in vacuum. So that was my model for dark energy. And that is because we have what are called Maxwell's equations of electromagnetism. And in a vacuum, when there are no electric or any other types of forces, one would expect that the solution of the Maxwell's equation would be zero. This is one way of looking at it. However, there is another solution which is non-zero. And that solution of the Maxwell's equations, we can say, would represent a 0-point field. All this happens because, contrary to what we think, that in vacuum, when there are no forces, there should be no movement. Contrary to that thinking, given all those things, vacuum, no forces, there are fluctuations, which are called quantum fluctuations. Fluctuations are very different from the usual forces which we encounter. Fluctuations are just departure from usual behavior. Next. So we can go on and on about why the 0-point field arises. Please, next. Next, please. There is a beautiful experiment that also brings out this feature, and that is called an experiment that was proposed by H.B.G. Casimir. I think Casimir is also from Copenhagen.
No.
No?
Casimir is from Poland.
From
Poland.
Poland. So Casimir,
I am not sure, but I sent it this.
he had proposed an experiment. You take two gold leaves, very thin gold leaves, keep them in vacuum. No forces, nothing acting. One would expect the gold leaves to remain like that. Instead, they keep moving away. Out of nothing, it is like magic. Imagine a magician who can pull out something. Now we know how he does it. There is some string, concealed string which he pulls, it comes on. But suppose I just do like this and something comes in. Not that anybody has done it, but suppose. That's magic. And 0-point field is like magic. So, the 0-point field, however magical, has very, very concrete, even experiment manifestations. For example, there is what is called the G is equal to 2 factor. When an electron spins, it spins in a very different way from a top. Or if you're standing and you spin, if you spin once completely 360 degrees, you're back where you were. But when an electron spins, if you spin once completely, you will be facing the opposite direction, as if you have spun only 180 degrees. You will have to spin twice to come back to the point. So it's called the G is equal to 2 factor. This is also caused by the 0-point field. So many puzzling manifestations. Next. Next. One way of describing such a vacuum I have found is a description in the Rig Veda, which says it's neither existence nor non-existence. We are normally used to thinking that either something is or is not. Non-existence is vacuum, existence is non-vacuum. But this seems to be a mid path, neither this nor that. Next, please. Right, next. This is basically a description of the 0-point field as it was known for the past 100 years. Next. Next. Well, I will not go into all this except to say that the quantum vacuum has been used by others. For example, Zeldovich, as Professor Larissa was mentioning, he used the quantum vacuum to get a cosmological constant, that is, an acceleration of the universe. But his problem was, and this was noted by others also, the cosmological constant or acceleration was so great that the universe would disappear in no time.
Yes.
Even as the universe came into existence, blown out. Which of course is unacceptable because we are living in the universe still. So these ideas did have some flaw. Anyway, next. But by taking the 0-point field as primary, as the starting point for the universe, one gets to a different interpretation. In fact, you get what is called stochastic electrodynamics, which includes random dynamics.
Yes.
That is something happening not by Newton's laws or not by any of these laws, but by some of these random forces jiggling about. Next, please. Next. Einstein himself had some sort of a belief in this type of a quantum vacuum or ether or whatever it is called. These were different names, but basically they were referring to the vacuum which was unvacuum-like. Next. Okay, next. I will go over all this, but I would like to quote Wilczek, who got the Nobel Prize a few years ago, American physicist. He quotes, his quote is, Einstein was not satisfied with the dualism. He wanted to regard the fields or ethers as primary. Einstein's problem was,
What means dualism now? What?
in those days, you had matter and you had ether. The two were separate. So Einstein didn't like that. He felt you can't have two things. They must be related. The ether or the quantum vacuum and matter. Next. We now come to an aspect that becomes very interesting. If a cosmological constant is caused by the 0-point fluctuations which are there everywhere, no place can escape it, then the acceleration of the universe is the first signature or first footprint of this dark energy, as we today fashionably call it. But is there a second signature or footprint which we can see? Well, there is, because what does this vacuum energy or 0-point field do? You take an atom, take a hydrogen atom, it's the simplest, proton at the center with the electron going round it. We know how the electron goes round the proton. That is the topic of quantum mechanics. For 100 years, we know exactly how it happens. What are the energies which the electron has as it moves and so on. But over and above all that, the 0-point field or a quantum vacuum buffets the electron as it does there. So apart from the electron going around the proton because of the electromagnetic forces, we have to consider this type of a random jiggling of the electron. And this random jiggling has been measured experimentally. It leads to a small shift of energy. This was observationally confirmed by two people, Rutherford and Lamb. And for this, Lamb and Rutherford got the Nobel Prize because they could experimentally observe that the electron is going round the proton, no doubt, but not exactly as our laws will tell us. There are small shifts, and it was explained that these small shifts are done by dark energy or the 0-point field. But exactly how, really speaking, could not be explained. They said it is this. A sort of an explanation was given. How the 0-point field can cause these shifts in energy, and that shift itself was measured. It comes to, about 1000 megahertz, which corresponds to a radiation of wavelength 30 centimeters. Now 30 centimeters and above, these are all radio waves. If you have less than a few millimeters, if you have, these are called microwaves. And these are called radio waves. Now remember, the cosmic microwave background was discovered in 1965 by Penzias and Wilson, for which they got the Nobel Prize. But when they discovered it, they didn't know what it was. They were radio engineers who were asked to create an antenna which would be totally disturbance free, and the poor engineers failed in their job because they could not get such an antenna. They even cooled it with liquid helium, thinking that now there will be no disturbance in the antenna. But still there was a disturbance. So they were completely puzzled because ultimately they couldn't deliver the goods. At that stage, some friend wrote to them that, look, there is a theory of the universe far away from radio engineers called the Big Bang theory. And according to the Big Bang theory, there was a lot of radiation when the universe was born. Slowly the radiation has dissipated. And a great scientist called George Gamow had calculated what would be the wavelength of the radiation now. And the wavelength turned out to be microwaves, exactly what these people had discovered without knowing it. So there was no way Wilson and Penzias could have eliminated that disturbance, because it's there in the universe. You will have to destroy the universe to get such an antenna. So finally they realized this, and then of course they got the Nobel Prize for this experimental discovery. These are not the same thing. These are radio waves. Microwaves are, quite powerful compared to radio waves. You use the microwave oven. Radio waves, on the other hand, are much weaker, not that energetic at all. Now, there is a big problem in discovering radio waves, and that is the Earth's ionosphere. You know that the Earth's ionosphere behaves like a mirror, which is a good thing. That is why we are having radio communication. You send a radio wave, goes up, gets reflected from the ionosphere and comes back. That's how you're having all these years your short band, medium band, all those things. Because of the ionosphere, which doesn't allow the radio waves to escape. But conversely, if radio waves were to reach the Earth from outer space, then the ionosphere will reflect them back. Not microwaves, we can receive them here, but radio waves very difficult to receive from outer space. So, an experiment was devised a few years back, and this was called the Arcade experiment by NASA. It was a balloon-borne experiment. The idea was to send a balloon to a height of about 40 kilometers.
But radio telescope, spaceship?
Well, spaceship didn't observe, they didn't have the instruments. Nobody expected this. Nobody expected. When the Arcade... No, they didn't have these detectors for radio waves. Well, they didn't find anything there. The Arcade experiment, when the balloon went up, what was it trying to find? We know that there are sources of radio waves in the universe, like quasars. You have heard about quasars? They emit radio waves, very powerful radio waves. Planets also send out radio waves, like the planet Jupiter. So, the arcade experiment was basically meant to pick up the radio signals from such events in the universe. What it found was a complete bolt from the blue. What it found was what the researchers called the space roar. It was radio waves coming in about this region of 1 megahertz. It was radio waves coming uniformly from all directions and very homogeneously. If you are getting radio waves from a planet or a star or a quasar, it will be very specific. It won't be uniform. It won't be like the cosmic microwave pattern. And this is exactly what Arcade 1 and 2 found, which is still, of course, a big mystery. But there's no mystery. It is nothing but a manifestation of dark energy or the zero-point field. If you give big names, then it becomes very difficult to imagine. But if you give it simple names, if you understand it and give it simple names, then it's easy. This zero-point field is there everywhere in the universe, and it causes these lamp-ship type of phenomena everywhere. So you expect a uniform radio wave background, and that indeed has been found. So this is another signature of dark energy, and hopefully this will be studied more and more over the years, because it's still relatively very new. I would now like to conclude with a brief comment, next please, on black holes. We have lived with black holes for 100 years, and one of the mentors of black holes has been Stephen Hawking. Suddenly, a few months back, Stephen Hawking suggested that there are no black holes. In effect, that is what he meant. Why? Because with black holes, you have a paradox which you cannot explain, called the information paradox. Now, what is this? We know that a black hole is something which only traps particles, radiation, everything. Nothing can escape from black holes. So if anything comes near a black hole, it is sucked in. However, Hawking had shown that there is something called Hawking radiation. It is not entirely one way, but it's also two ways. So, what does it mean? If there is a black hole today, it is collecting all the information, but also slowly, through Hawking radiation, it is getting destroyed. And one day, it will get destroyed. There will be no black hole left. There is something wrong with this argument, because so much of matter means information, so many trillions of bits of information are inside a black hole, and if the black hole evaporates, what has happened to all this information? That is the black hole paradox. There is no way we can explain it. So Hawking recently said, all right, let us assume that there is no such horizon of a black hole which traps all the information, which means that there is no black hole. then the black hole information paradox also disappears. This was one approach, but my work of some 10 years ago already was hinting at this from a completely different point of view. Next, please. Next. 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 This is the information paradox. Next. Now, what my work had shown is that if black holes exist even for 1 second, then they must be millions, not millions, but billions of times as massive as the sun. These are called supermassive black holes. So only supermassive black holes have a chance to exist. That is provided my theory is correct. And even then they will exist for just a fraction of a second. The extreme cases, if the black hole has all the mass of the universe, if the universe itself were a black hole, then it would live like what we are living now. But otherwise, fraction of a second, even for supermassive black holes. In other words, no information paradox. Next. So this is the mathematical relation for the lifetime of a black hole. Next. Now, this conjecture that there are no black holes has received surprising support from another physicist, a lady called Laura Mersini Houghton of North Carolina University. She has made detailed calculations and has concluded that black holes cannot form. Why? Yes. They cannot form because as a black hole is forming, matter is collapsing to form the black hole. But soon the Hawking radiation outwards is kick-started, and she has calculated and shown that the Hawking radiation which goes out neutralizes the black hole that is collapsing, and the net result, no black holes. Surprisingly, my friend and collaborator Walter Greiner of Frankfurt, he also comes to this conclusion from yet another point of view. His concept of space-time is a bit like my own concept. He calls it the pseudo-complex space-time. And in his theory, there cannot be black holes. So after a century of black holes, suddenly, from 4 different points of view, people are arguing that there are no black holes. These are purely fictitious, fantastic objects that have no place in the real world. Now this is not a nice thing because so much of research has gone in. The entire subject of general relativity encompasses this. And now if we say that on physical grounds there are no black holes, then once again that will open up a lot more results and a lot more research. So exciting things are always happening in the realm of the universe and physics, and I wanted to give you a glimpse of 2 aspects of this. Thank you.